Good morning to all of you. So today we are going to start new topic, that is electron paramagnetic resonance. Not entirely new because initially I had as a magnetic resonance I have discussed both these concepts. It is basically the magnetic interaction of electrons and protons with the external magnetic field. So and the protons are the nucleus, the way we have understood. So once you have understood NMR in detail, it becomes easier to discuss electron paramagnetic resonance, because it is the we were looking at the magnetic precessional frequency of nucleus when it is put in the magnetic field. Here we are talking about the similar precessional motion will be set up in an electron due to this magnetic moment. Magnetic moment is there because of the two reasons, one due to the spin and another due to the orbital motion. So both these factors will be here in case of electron. So these fundamentals were discussed in my previous classes when I just started the discussion on magnetic resonance as a general concept. And then the magnetic resonance has two parts. You have the magnetic resonance of the nucleus and the magnetic resonance of the electron. So this is the second part that we are going to deal with. So was the very beginning. If you go through my previous class lectures, which is available, uh, which has been shared with you, you can still understand what is there. So orbital, so the two things that contribute to this angular momentum, and so this was the point that is coming additional in this particular. Spin was there for the both things, nucleus as well as electrons, but orbital motion is only something that we are considering here for electrons. And these things will electrons, so magnetic moments will arise because of this motion. So they, as I told you in previous class also, the electrons behave as tiny magnets. They are themselves, and when I say magnet, any magnet is a dipole. It has a north pole, a south pole. So it is a dipole, and this concept I have already discussed at length at a very um, long discussion I had on that topic about this magnetic dipole. Right? Every magnet that you see in life is a dipole, and the same thing is true for the smallest component, that is electron or nucleus of any substance. So an electron, which is an electrical monopole, when you put it in magnetic field, it behaves as magnetic dipole. Right? You cannot have a separated north pole, a separate south pole. That's impossible. So that's so magnetic monopoles do not exist. This also I have told you. So these are the fundamentals that has been discussed earlier classes, and so we can move on to the next part, that is, so the energy dependence. We found this that the magnetic moment into the magnetic field. So this gives you the energy of interaction, and based on that we discussed how we can formulate a Hamiltonian. We can formulate a magnetic moment operator, and then so that will be the Hamiltonian to represent the system. So you can have, so what we have discussed this, what is this I and S, these are the angular momentum. So this is the angular momentum due to orbital motion, and this one is the angular momentum, again same thing. but this is due to spin. So we call it spin angular momentum. So S, and the magnetic field that is generated is proportional. Magnetic moment is proportional to this I, that is the angular momentum, orbital angular momentum, or it is proportional to, it is also proportional to S, which is the spin angular momentum. So, and when you remove this thing, proportionality constant, you bring in the this terms, this equivalence is there. So this is the gyromagnetic ratio, and in case of spin, there's additional factor of 2, which is the G factor, which is it was found that whenever you calculate the theoretically the magnetic moment, if you calculate by the formula and remove the proportionality, you always found that exactly double the value. Experimentally it was found that it is double the value of that magnetic moment, and so this 2 was additionally the factor of 2 was coming in, and it was added to this equation, modified equation, to account for the actual thing, actual what happens to the uh, magnetic moment. Okay, so this 2 is actually coming from this is coming from what, coming from the relativistic effect, theory of relativity. So relativistic effects accounts for this G factor. So, effect. So due to that there is additional, so always spin angular momentum generates a larger dipole, and so you see, so fundamentally for an electron, you see this arrow is bigger, this arrow is bigger. Why? Because this is the green one, the magnetic moments, and the magnetic moment due to the spin angular momentum is much larger than this thing. So you see, whenever you draw diagrams, let your pictures speak for themselves. So you see here the angular momentum I, which is orbital, due to the orbital motion, was larger, big arrow. Angular momentum S is smaller arrow, right? So this is both about electrons. So but when you are calculating this thing, you find that this is much longer as compared to the original angular momentum. So that is because of this factor of 2G that is coming in. So this extraordinary length that you see here as compared to S is, that means the magnitude is much larger, and that is represented by the length of arrow vector. So whenever you draw vectors, the arrow, the length represents, length of the vector represents the magnitude, and how you place the arrow, that is the direction of the vector. So it's like that. So that's how you keep the things and make it. So this proportionality constant that we introduce is called gyromagnetic ratio. We just talked about this. So this gyromagnetic ratio is given by, for electron it is E by 2me. For proton you can replace the mass, and the negative sign will be, negative sign appears because of, negative sign because of the electron is negatively charged, uh, negative sign as electron is negatively charged. For proton this will be positive, usually positive. So magnetic gyric ratio and the mass of electron is replaced. So this is something that we have already discussed in previous classes. And then with the relative orientation of the spin vectors in with respect to the orbital angular momentum also affects the overall energy of the system. So we have previously discussed the thing that if both the I and S point in the same direction, that will give you a high energy setup when you apply a magnetic field. that is so suppose if you have an applied, when you apply a magnetic field V naught, so this one will be pushed up, this will appear higher in energy, and this one will appear lower in energy. So you can see, so this is, so in absence of any magnetic field, the two will have same thing. Yeah, the relative orientation. So total angular momentum is, when you calculate, so it is the relative orientation of the momentum which gives rise to total angular momentum of the electron, and that has implications for the energy of interaction. So when the two are, see, when the two are parallel, that is giving you high energy. When so lower energy setup is anti-parallel, that gives you low energy. So this is the configurations that so spin angular moment and okay. So also we also know about this, that we the spin vector can be placed on this cone when it is ms plus half, and anywhere on the cone, whether I place it here or here, the z component is still the same. That is, z component is still, z component is always equal to ms h cross. So this is still the same. With anywhere on the cone you place an arrow, the vector, length of the vector is same, the z component is same. Only the other, the angle, sorry, this x and y values are changing. So z component is fixed, so orientation can be any of the, like this. So anyway, so similarly you also know how to place the, if you say spin minus half, that means ms is minus half. So, and you also know that the magnitude is given by s. So this is the z component that is given by plus half or minus half. This is my ms minus half h cross. So this is how you relate it. And previous, so this was only the z, when you apply a magnetic field, only the z component is going to matter. And earlier, while discussing in previous class, many classes prior to this NMR, we had discussed this magnetic resonances at length uh, in greater details. And I told you that it is only the z component which is lying along the B naught applied magnetic field that is important for you. So only take the z component of the angular momentum, only the z component of the angular momentum counts for calculation of magnetic moment. Okay, so just a moment. Okay, never mind. So these are basics which I have already discussed, and yeah, you can go through previous lectures videos and you will find that these are the things that we have been discussing all along while discussing the magnetic resonances. So only the z component is to be taken. So if you are talking about the angular momentum due to orbital motion, so that is the Lz mlh cross is the z component, and that's what counts for your purpose. So your magnetic moment is given by the z component of the angular momentum and the guiding magnetic ratio. Energy is then mu z. This mu z is coming here, multiply with b naught applied magnetic field. So Then the energy consideration. So energy consideration is coming in when you have an external magnetic field. Unless and until you have external magnetic field, this different ml values do not, the magnetic quantum numbers for the ml do not have different energy. They are all degenerate sets. So only in presence of magnetic field you will have this energy separation will be different depending on their components. So ml h cross, this is how it depends. So energy of the, so if you're talking about p orbitals, ml values will be different for px, py, pz, and similarly the orbital motion, due to the orbital motion, this will be the energy difference arising in each one of them when it is ml is 0, ml plus 1, ml minus 1. So that's how you understand these things. And then there you simply rearrange the equations and put it like this. Then it is called mu b, the Bohr Magneton. Mu b, sorry, it's going beyond the screen. So this is your, so this is sorry, and then so this mu z that we are talking about is something, sorry, so this eh cross by this 2me, this is your Bohr magneton, each by with a negative sign. And this Bohr magneton is the basic quantum of electron magnetic moment. So that's how we start with the things. And so Bohr magneton, here how we define it. Mu, the, you have this gyromagnetic ratio and the h cross. So with a negative sign, mu gamma e h cross is giving you the Bohr magneton, which you can calculate to be like this. Fundamental quantities. This is something we have already discussed. Similarly, so that this is something that we derived using the angular momentum due to orbital motion. Same thing you can define. Similarly, you can also calculate the spin magnetic moment based on the concentration of spin angular momentum. And again, you will have to take, you have to only worry about the z component. Okay, and here additional thing that comes in is with the g value, which was for, so we are talking about an electron which is an isolation, and that will have only spin. Spin is inherent to any system which is any electron which is not part of atom, that also has spin, and therefore it will have a magnetic moment. So this factor of g is additional. So this is the difference that comes in when we are writing the equation magnetic moment for the, due to the spin angular momentum. In addition to the gyromagnetic ratio, we have Ge as subscript E represents for electron, G value for electron, a free electron, which turns out to be something like this. So you always get twice, practically when you measure the magnetic moment, you get twice the value of a simple calculation that gives you gyromagnetic ratio into the spin angular momentum. So that is the consideration. So because you have electromagnetic field is fluctuating in the vacuum, and that, so that that way, so this is taken into account through that factor g values. So this thing plus half h cross ms plus half ms minus half. So we assign alpha and beta state that we have already discussed. previous classes. So if you go on simply adding putting the terms together, you will get again gamma e h cross ms mu b and Bohr. So that Bohr Magneton is already defined. So you have, so the when you apply external magnetic field, on application of external magnetic field, the vector will start precessing. This vector will start moving along this path, along this cone. The tip of the vector, if you trace it, it will be going like this along the cone. So this is the precessional motion. Mind it, earlier when no magnetic field was applied, it was not precessing. We were only talking about that the vector can be placed anywhere on the cone. But when we apply magnetic field B naught, then it starts along the z direction. So when the B naught is applied along z, the vector that we are seeing, this arrow, it starts moving in along the cone. That is the precessional motion, and one complete circle is the that we call, you can calculate the frequency, so how much time it takes. So that can be calculated frequency. So in 1 second, how many such one complete motion along this circle it can do it. So that is mu e b naught by 2 pi. So this is the Larmor frequency. So Larmor frequency, if you just do a rough calculation for simple 1 Tesla field, then it turns out to be 30 gigahertz. So put b naught is equal to 1 Tesla field, then the frequency is 30 gigahertz. So clearly a difference. So at the same 1 Tesla, a proton was giving you something around much lower frequency. So that was falling in radio frequency region, but this one is, it falls in the microwave region. So this was the case. Here this was to show the precessional motion of a nucleus. So plus sign you see at the thing, but in a similar way you can also imagine what can happen to an electron. So this is when the energy is frequency is observed. So this was with respect to nucleus. So once you have understood how the nucleus behaves in a magnetic field, same thing except the direction will be changed. So what was plus so lower energy, so because electron is negatively charged, so because of that the directions are different, but this concept is similar, that it is spinning in one direction along the one cone. Now it is precession is happening. Now when the energy is given here, in case of electron it will be the microwave energy, not the radio frequency. That's the spinning motion will undergo a change, and so the energy that we can discuss here is in terms of alpha and beta spins. So you have energy level due to ms minus half, ms plus half, and so the separation energy level will be is slightly different from what we had seen in protons. So here you have plus alpha. Alpha is of higher energy, beta is of lower energy. So plus half higher energy, minus half is of lower energy, beta state is lower because of this thing. So these are the things that we had previously discussed. So normally the magnetic field that we use is about 0.3 Tesla in commercial spectrum EPR spectrometer. So and then the transition that you can explain, and when you apply this field, the frequency, it turns out to be around 10 gigahertz. So this 10 gigahertz this is a microwave, this falls in the microwave region, and so so EPR is typically a microwave technique. So the interaction is happening with the magnetic dipole interacts with magnetic dipole in the electron. Electron, it behaves as a tiny magnet. When I say magnet, it is a magnetic dipole. The magnetic dipole, and that is what you calculate, the moment. When you say that magnetic moment, that it is a dipole moment of the and that thing, a magnet, dipole moment of a magnet. So that is so the energy of the precession, the frequency of precession falls in the microwave region, and so if you irradiate with that electromagnetic field, absorption will happen, and so that is what we analyze in which is in electron paramagnetic resonance. So it is the magnetic field vector of the um, uh, electromagnetic wave, the microwave. So magnetic field vector of the uh, interacts with the this magnetic moment of the electron. Okay, so this is a point of difference, because microwave is also used for rotational spectroscopy of a rotation of a molecule, but that was interaction of electrical electric field vector of the radiation with the electric dipole. Here it is the interaction of, mark my words, mark my, many students, many people do not know this difference. There you use microwave for rotational spectroscopy, rotational right? You have already read in third semester, even in this semester you have that thing, microwave spectroscopy. That was rotational, in relation to rotational spectroscopy, right? Rotation of molecules also falls in the microwave region. But what is the difference between the two? So in this particular, in case of EPR, it is the magnetic field vector of radiation that interacts with the magnetic dipole. In case of rotational spectroscopy, it is the same the microwave, it is the electric field component of that uh, oscillating uh, electric field vector, which interacts with the electric dipole, right? So so this is the difference that you have to understand. You need to understand this. So it is very EPR is useful for what kind of samples? If you have free radicals, unpaired electrons, anything that has unpaired electrons, that will be, you will get much more very good information about the structure and geometry, many things you can predict if you have this data, EPR data. So studying radicals in chemical, formed in chemical reactions, it is very helpful for radicals have unpaired electrons, so many d metal complexes have unpaired electrons. So molecules in triplet state, so you understand oxygen is triplet, it has unpaired electron. So things like this will be very, so understanding becomes easy if we do EPR, perform electron paramagnetic resonance spectroscopy on such species. So we can have gas, liquid or solid, but uh, it is in gas molecules it is very difficult, because rotation of the molecules complicates the overall situation. So you, if you fix the thing and then analyze the spin, then analyze the magnetic moments, it is easier. So a typical EPR spectrometer is, looks like something like this. It has a microwave source, okay, and here is the sample, and the two electromagnets. So electromagnet is placed, so this huge structures magnet, this is your magnet, right? And the small thing that you see that is put between the cavity, this is the sample, this is the sample placed in over here. So what we are seeing, the microwave source, so it is the B naught B oscillating magnetic field vector. This is what interacts with So microwave source, so microwave radiation has this thing in it, and this will interacts with the magnetic field, with the magnetic field, the magnetic moment of the spinning electron. Electron, the tiny magnet. Understand it this way. Electron, a tiny magnet, that is a magnetic dipole. It is a magnetic dipole that we are talking about. So this is how you have to first fundamentally understand the thing. So you have oscillating magnetic field component in the radiation that will going to it. So just like we talked about in NMR, there is continuous wave CW mode and FT Fourier transform spectrometers. So continuous wave spectrometer is, there is continuous irradiation, and you can scan different frequencies. Okay, you separate one by, so each one of the frequencies falls on the sample one by one, so that is a continuous wave mode. And FT is just you give a short pulse and then do analyze the to deconvolute the this pulse after it has been absorbed. The change in pulse profile can be analyzed by Fourier transformation, and you can convert it into this thing. So you can convert into the normal spectrum, that intensity versus frequency thing. So that is the normal appearance of a spectrum that you can think of. So the fundamental difference between the two type of instrument is similar to what we had discussed in normal field scan mode of the continuous with NMR, and the Fourier transformation NMR. So the things are similar, except that we have a microwave source instead of a radio frequency. Okay, and rest of the things, the basic idea of analysis remains same. So this is the layout of the spectrometer that we have already discussed. A cavity is there, and you have a source of microwave, then you have a source of microwave, and then the detector, which can microwave detector, and the field. So you have a very, in the region of 0.3 Tesla, the electromagnet can generate magnetic field. So there are various frequency ranges that is available for EPR spectrometers, and accordingly their name has been, different bands of microwave region has been defined in accordance to that. And so you can have this S band, X band, Q band, but most important is the X band spectrometers. Most of the analysis is done with this. So you have a wavelength of around 3 centimeters, and the V 0.339 Tesla, frequency is 9.5 gigahertz. So around this we build up the whole thing. We start with this. So this is a typical EPR spectrum. This is how a typical EPR spectrum looks like, and this is for a benzene radical anion. Benzene. So benzene, if it gains one electron, this is minus charge, that you can see 6H6 minus. So of course the 6 will be subscript. So you are getting 1, 2, 3, 4, 5, 6, 7 peaks of varying intensity. So again the idea remains same. You can what you are seeing here is the splitting of the signal into 7 different components. So this is due to the interactions with the you have 6 protons that you have. So one unpaired electron interacts with the protons which is present, 6 hydrogen, and that's how they split due to these interactions. You also see a difference here, that we are not taking the intensity directly. It is the derivative plot. Basically it is derivative, first derivative of the signal di by dx, field, if you write as field strength. So so you can think of this, let me write dx. So field, you can x can be your field. So it is a derivative plot, not I versus x. And so it is not simple plot of I versus x. It is a derivative plot of, say, x, something like this. So this is I versus x, this is di by dx. So that is what I mean. So the derivative plot is, so this has nothing to do with the, so although the actual spectrum is obtained in form of this, but simple intensity versus frequency or field strength, but you can convert it into this kind of pattern, and this is a typical way how an EPR spectrum will look like. So here we discussed, in case of electrons, we discussed the G values. That G value was typically for that was for initial, what we discussed. So that splitting pattern that you are seeing here, this A is the hyperfine splitting constant. The splitting that we see here is called hyperfine splitting, that arises due to interaction of the unpaired electron with the magnetic nucleus. So how many magnetic nuclei here is? There's 6 magnetic nuclei, and so H hydrogen, the proton, is magnetically active, and so you are having this pattern of splitting that is happening. There is the hyperfine splitting constant, just like you had the, so this arises due to this interaction between the. So what you saw in the previous slide was, this is what I was trying to tell you, that initially you obtain a signal. So in terms of, if this is the A plotted versus B, this is the normal absorption of the signal, and this is the profile that you obtain. Absorption divided by on y-axis, and you have this field B which is on x-axis. Okay, so this signal, you can plot the slope, you can take the slope at each point, which is dA by dB. So here at the top of the peak, where peak appears, if you plot, you will get dA by dB is 0. So this is 0 plotted over here. You look at this, dA by dB is positive. So you see, you plot it here. So this particular point is here. So, and similarly, if you plot at this point, dA by dB is negative. So you see, you get plot this here. So in this way, if we take first derivative of the spectrum, we calculate the dA by dB, the first derivative at each point, we can generate a spectrum which will look like this. Okay, so this is the first derivative of the initially obtained spectrum absorption signal. So this is a technique. So in case of EPR spectrum, this is usually done. It is the first derivative which is plotted as the signal you see. So you have Uh, so so what is the point to note is that where there was a peak position in the actual signal, there is a it is 0, it becomes 0 in the derivative plot. The derivative in the derivative plot, the peak appears as a 0 value over here, and the slope is highest, so the two apparent peaks represent where the change in absorbance is faster faster than other points. So that is what is doing. So fastest change in that particular, as the field is varied, the fastest change in that appears at this particular point. So it is the change in signal, and this is the maximum obtained signal. So this is the peak is here. Look at in the first derivative. So peak of the absorption sig corresponds to the point where the derivative passes through 0. That is the important point that we have just learned. And you can very well ask your question that why we are taking the first derivative. So there is not much reason attached to that. Historic, it is more of historical than scientific. Okay, so yes, we could have done without doing that, but initially it was the experimental factors. Initially people thought, because of which people thought that it is better to take first derivative rather than taking the original signal, this intensity versus magnetic field, or intensity versus frequency. So it is because there was a baseline shift observed in initial early EPR spectrometers, which was dependent on applied field. So to avoid that, that factor was eliminated when they took the first derivative. So the thing is still, the convention is still followed, and we have all the EPR spectra usually reported in first as a first derivative format. So this is this is the pictorial summary of what we have discussed just now. So it is, you have this initially, okay. So you have, so you apply magnetic field, the something that was plus half and minus half, which was ms plus half or plus minus half, was having same energy initially. In absence of magnetic field, it now becomes different. You have alpha and beta split, so energy difference. So now you have beta to alpha, transition will happen. Sorry, beta will be of higher energy in case. So plus half and minus half. So this will be the situation that we had just discussed in previous slide. So this is the same thing that we discussed here. Just a moment, where we discussed. So, so the energy, yeah. So we have discussed how the energy will be affected. So alpha, beta is so as we discussed earlier, why we have alpha which appears at higher energy, plus half and minus half. So the placement of the angular momentum and the magnetic moment point in opposite direction because of the gyronegative charge. The gyromagnetic ratio is, you also have a minus sign along with that. And so when you analyze this thing, so you have alpha is of higher energy, beta is of lower energy, and if this transition happens, if you give this microwave appears, so we have microwave and that is absorbed, the transition happens, so absorption, microwave comes in, absorption happens, and you get a signal like this, absorption signal. Then take the first derivative. So now you know how you can do it. So there is algorithm, you can do it in origin with in a click, in a flash. You have done for pH, you have taken first derivative for the pH versus volume plot. In a similar way you can also do this absorption versus magnetic field if it is plotted. So you have so this is the magnetic field plotted along this, and this is the absorbance. So absorbance A versus B. So and then taking the first derivative, it is dA by dB versus V. So this is the how we obtain this signal. Okay, so the G value that we discussed for free electron, that was yeah, it was for a free electron, the relativistic effect. But the same thing will change for if the surroundings, if the electron is a part of an atom or if it is a part of a molecule. So the G value is for the electron is very critical thing, and it somehow depicts, it tells you about the molecular environment. So different free radicals that we can talk about in organic chemistry or d metal complexes which have unpaired electrons, they all have the G values does vary because of the surroundings have changed. It is not a free electron anymore. So we can discuss it tomorrow, the G values, how it will change in the different circumstances, and then some more on the splitting patterns, the fine structures, the interaction of the electron with the neighboring nuclei. So all those we will cover in tomorrow's class. Thank you.